Okay, so over the last two segments, we've done the hard work of, first of all, defining what functionals are, observing that we can define a free energy functional in the context of elasticity problems. And then we've also gone ahead and constructed a notion of a derivative of a functional with respect to a field. And this we said we wanted to do in order to be able to talk about extremization of free energy functionals and thereby talk about equilibria. Okay, so now we'll, in this segment, let's just apply it to our functional. All right, so extremization of pi, right? Let's actually compute it. We know how to do it, right? So here's what we want to do. What we want to do is find u belonging to S such that, now remember that that variation that we constructed was based upon our field W, right? But W was really meant to just give us a certain type of variation, right? Therefore, what we want to say is that when we try to find the extremization of pi, we want to find the extremal point, right? So we want to find this field U that extremizes pi, but for all possible variations, right, in a certain class. So what we say is that we want to find U belonging to S such that for all W belonging to V, right, and recall that S satisfies the, remember S consists of U such that U at 0 equals U naught and V consists of W such that W of 0 equals 0. Okay, right. Find U belonging to S such that for all W belonging to V, the following holds, right? dd epsilon of pi U sub epsilon evaluated at epsilon equals 0, right? Let's do the extremization. This is the derivative that we've written out. What is the extremal condition? The derivative vanishes. Okay? Let's do this now. What this implies then is that dd epsilon of pi, right? And I'm going to write out pi. And let me give myself big enough brackets here. Okay, dd epsilon of integral over omega. Okay, here we have 1/2 E A. Now, it's not just U, but U plus epsilon W, the whole thing, comma X square dx minus integral over omega f times U plus epsilon W A dx minus T A times U plus epsilon W. Okay, all of this, right, we take those derivatives, set epsilon equals 0, right, and then say that all of this should be equal to 0. Okay, that's what we need to do. Now, observe that in computing this derivative with respect to epsilon, the integral really does not pose us any problem. And this is because epsilon is not a field, right? It's just a number. If you were to actually go ahead and compute those integrals, you would get some value depending upon epsilon being a real number, and you would just differentiate with respect to epsilon, right? So we're actually free to take the derivative with respect to epsilon into those integral signs, right? What this implies then is the following, right? Okay, we have here, right. So now let's take this derivative inside, right? So we have here integral over omega 1/2 EA. Now, because of that square, we get 2 U plus epsilon W comma x, right, times W comma x, right, dx minus integral over omega f times W A dx minus TA times W. Okay? All we've done here is recognize that epsilon belonging to real numbers is just a, right, it simply multiplies out each of these integrals. So we're free to take the derivative with respect to epsilon into the integral sign, and this is what we get, right? So now after computing all of this, we have to set epsilon equals 0, all right? And then the extremization condition is that this result is equal to 0. And just to make it clear, let me draw a partition here between the previous line and this one. Okay? Now, of course, there's some simplification that one can get. Okay. All right, now, using epsilon equals 0 in what we had on the last slide, which is right here, okay, we observe that epsilon shows up in only one place here, right? So setting epsilon equals 0 will reduce this integral to the following form. Integral over omega. Now, we have EA u comma x times W comma x dx minus integral over omega f W A dx minus T A W. Okay, this is what we get by setting epsilon equals 0. The extremization condition is that this is all equal to 0. Okay, as a final step, I'm going to reorganize this, just one of these integrals, into the following form: W comma x EA u comma x dx minus integral over omega W f A dx minus. Oh, I just realized that here we had, since we had u evaluated at L, what we get here is W also evaluated at L. Okay, and so it is on the previous slide as well. Okay, so here we get W at L dot T A, right? All of this equals 0. All right, Now you may have already noticed it, but then what we have here is, thanks to our constitutive relation, it's just sigma. Okay. So finally we get integral over omega w comma x sigma a dx minus integral over omega wf dx, but there is an a here, minus w at L Ta equals 0. Okay? And you recall that this is the condition we said must hold for extremization for all W. Okay? And you recognize that what we have here is simply the weak form. Okay? So it is that when we have working for us a so-called variational principle, right? And in this case, the variational principle is that the free energy functional is extremized. Right? When we have that variational principle working for us, we can indeed derive the weak form from a using these so-called variational arguments by starting out with the energy functional, the free energy functional. So, remarks. When an extremization principle is available, right? And in this case, what is the extremization principle? It is the extremum or extrema of the free energy. Okay. So, when an extremization principle is available, the weak form can be obtained using variational calculus. Right, and often this is combined into saying that a variational principle exists, right? One says, therefore, that a variational principle exists. Okay. Let me see. All right, so this is a useful thing to know. Now, what we see in this case is that, of course, we get back the weak form when we invoke elasticity. However, we also know that the same weak form works for other problems as well, right? It works for heat conduction, it works for mass diffusion, right? So one can ask the question, what about those problems? The fact of the matter is that there does not exist a physical variational principle for problems of heat conduction and mass diffusion, right? At least not one that talks directly of extremization of certain free energies, all right? Some of these arguments are applicable to mass balance or to mass transport, but in a more restricted sense, okay? A separate series of lectures addresses that question. But anyway, so what about those problems? Well, one can use the same weak form but one cannot demonstrate that it is available, that it can be obtained from this sort of a variational principle. Therefore, we tend not to pose those weak forms as being derived from a variational principle. The issue with those sorts of problems is that the quasi-static or the steady-state problem is only a very restricted case of heat conduction or mass diffusion. The full time-dependent problem does not subscribe to an equilibrium state, and therefore these kinds of principles are not applicable. All right. Pertaining to that, I will state that this derivation is not appropriate for the physics of heat conduction or mass diffusion. However, the mathematics works, right? You may simply ignore the fact that a physical principle does not exist and just say, well, I don't really care. I'm going to define something that I call an energy or an energy-like quantity for heat conduction or mass diffusion, and go ahead with this process, right? So the mathematics works, but the physical principle does not exist, and therefore we tend not to present it as such. Okay, so let me just state that the mathematics, however, works. The fact that this principle of this variational principle exists for problems of elasticity is a very powerful one, and it is used to construct much more general and indeed more powerful finite element methods, variationally based methods for problems involving elasticity. Okay, and that is the topic of a more advanced class in finite element methods. I should probably also state that problems for which variational principles exist are the following, or at least some problems for which variational principles exist. For elasticity, right, in all its forms. Okay. Well, properly, actually, it exists for elasticity at steady state okay. Variation principles exist for elasticity at steady state, but once you talk about elasticity, whether it's nonlinear elasticity or linearized elasticity or elasticity with other constitutive conditions added onto it like plasticity or damage or viscoelasticity or other things, it works. Okay. Another problem for which it also works is the Schrödinger equation at steady state. Okay. Schrödinger equation, right, also at steady state. Okay, and therefore for these kinds of problems and some others as well, one can construct variational principles, one can construct basic as well as more advanced finite element methods using this approach. Okay, it does not exist, for instance, for problems of heat conduction, mass diffusion, like I said. Also the problem of fluid flow, right? For the Navier-Stokes equations, there does not exist a variational principle. All right. That's about what I wanted to say in this segment and indeed for this unit. At this point, we're done with everything we wanted to work on for 1D linear elliptic problems. In the following unit, we will embark on multidimensional problems.